Dr. Mbatha, thank you very much for being with us this morning. There is a large group that was very excited to listen to what you're sharing with them today. So please, you're welcome to share your screen and introduce yourself and start the presentation. Thank you very much.
Okay, no problem. So, can we share? I think I need this. You can see my screen now.
Yes, we can see your screen very nicely.
Okay.
Yeah.
Okay. So my name is Nkanyiso Mbatha. I'm actually I did my PhD at UKZN and SANSA on atmospheric physics.
Okay. So who was your supervisor, Dr. Mbatha?
I was working on the LiDAR that is at UKZN, and some HF radar program.
Okay.
Yeah. So, but it was mainly atmospheric dynamics and signal processing.
Excellent.
Yeah. So I'm now at the University of Zululand teaching atmospheric physics and chemistry for students who are doing atmospheric science. And recently I have because my expertise is much more on middle atmospheric dynamics and so on. I noticed that I can do much more when I go down to hydrometeorology as well and apply signal processing in some of the signals that they do, and also remote sensing and data science of geophysical data. So that's what I'm doing here now. So, and I'm really not, for many years I've been using MATLAB. However, recently I'm now using Python. So, I think Python is doing much more better work than the very long codes that I used to write using MATLAB. So MATLAB was asking for more from me. So here today I just wanted to, I'll do two things. My first idea was that I have this talk, show you how you can view spatial data inside Python using Python Anaconda and Jupyter Notebook or Jupyter Lab. So I'm using Jupyter Lab here. I will not go back on how you install it. I'm sure you have installed it and so on and so on. So I'm a self-taught Python person, which makes me better because I'm free to learn whatever I want to learn at whatever time I want to learn that. So what I've done here, I associated this short demonstration with climatology guys. So you have a lot of data already, especially your remote sensing data, your station data, and many other types of data, output of WAF. For instance, I'm doing a lot of WAF now, but I'm concentrating much on WAF Chem for chemistry modeling. So WAF outputs, how you view them, all the data science that you need to do this. So this talk, or this short demonstration here is based on that. And what I've done, because I know that you can get all this information for yourself, but I made sure that I put some links here of different things that I'll talk about that can make you better, including how you can install, or what you do. First of all, you need to have an environment in your Anaconda. So I created an environment which I call Geo, where I do geospatial analysis, geospatial statistics, and all those things. So you need to create that environment in your Anaconda and activate it, and then you can start to install many of these things. One thing that I wanted to talk about, of course, I don't have time. I don't think I'll try to be fast as I demonstrate what this is. But one thing that I wanted to talk about quickly before I go further is what is called GEE, Google Earth Engine, for people who want to do spatial data. It has atmospheric chemistry, it has meteorology, it has all the atmospheric physics parameters that you need. So what happened is that NASA, working together with Google, they created this nice system called Google Earth Engine. I can just demonstrate to you shortly. I'm sure some of you would like it. Maybe let me switch off my video. And so this, I need to, okay, so code. You open it by code editor. So, so let's opening this now. So I'm sure some of you may have seen that, but you need JavaScript to run all that. So you do a lot of spatial analysis there. I must say, as a person who has a background on JavaScript, I enjoyed working with this data. So there I'm working with different satellite data. You have all sort of data in the Landsat 8. Already there's Landsat 9 if you want to look at your land cover, land classification, and all those things. Already Landsat 9 data is in the system there. You can do classification, and you can see these are many different codes that I write on myself. Maybe let me show you one. This, okay, classifying code. Here I was doing image classification, and I do atmospheric chemistry as well. Calculating NDVI, drought indexes for climatologists, which are calculating using satellite data, of course, doing some spatial statistics or just normal non-parametric test methods on some time series inside Google Earth Engine. I have many of these small codes that I wrote, normalized differential drought indexes. So it means in South Africa, you can look at drought indexes that are calculating using satellite data. It can be MODIS or Landsat or Sentinel-2, all those different satellites. So it makes remote sensing much more interesting. For instance, here I was doing NO2 analysis. NO2, I will do it in 2 days' time in my next lecture, because in my next lecture, I want to show how you can, because here in KwaZulu-Natal, these friends of mine here looted, these guys looted here and so on. They took a lot of things from shop and they banned things. So what I did is to initiate a project where I look at the pollution from space during the banning. So that's what I will be showing next week. So these are classification. This is classification that I'm running here. I'm using random forest, but I can use CNN. I can use regression-based methods like SVM to classify land cover. So you can do a nice classification of any image and so on and so on. So this is the nice code that I wrote for classification using JavaScript. But let's go back to Python. Well, after not being happy with JavaScript, how you write and so on, I decided to actually maybe move more to Python, which is very good for data science and so on. So all this, I'm doing it, but not much. Maybe someone else can do it because of the intensity of coding that Java script requires and so on. But with Python, it is much more easy. So in this talk here, I'll talk about Xarray. This Xarray is a very nice tool or library to find in Python, which will help you with multidimensional data. It is directly related to NumPy, so it uses NumPy and pandas in there, but it can do what NumPy and pandas do, but it is much more geared for multidimensional data. So for details about that, I think I put in some links about it, and I also use it together with Dask. So this Dask provides sort of computational capability for your computer. It's a package that assists with computational capability, because some of these images are big. You need to run that as well so that you can do your spatial data much more faster and so on. So I also put in some different links for you guys to learn, because I noticed a few talks ago that most people were having questions about X-ray. So I made sure I put in a lot of information about X-ray, but there are basically two data formats, or main data formats of X-ray data structure. This is this one here, X-ray data array, and also X-ray data set, and so on. Yeah, and for Google Earth Engine, if you want to go look at it, these are the links that you can go to, and this is how you install things. I normally use CondaForge. If you are using a Windows computer, sometimes it is problematic to install some of these libraries. Hence, I use this computer that I'm using and my Linux computer here, which helps me. And then so first of all, of course, so to summarize what this is about, I took rainfall data, which is measured by mirror. If you want to know where that data is, there is a website where you get a lot of data for Earth physics and chemistry by NASA and by Copernicus satellites. So, for instance, I know most of you are doing modeling using math. So sometimes you want to compare your WAF output with different other methods or different other methods that they use to measure whatever parameter you may have been measuring. So this NASA disk website here gives you an option of very many different types of data sets that you can use for doing physics and chemistry of the Earth. So for instance, here you can see there's GPM data, there's TRMM data, there's chemistry data, there's UV data, there's all sort of data. So this data is now fully available. You just need to register with Earth data and then download it. For instance, the data that I'm using is MIRA2 data. And it is NetCDF, as you know, that your NetCDF files are easy to work with when you understand X-rays. Of course, this becomes a bit longer if you're using NetCDF library to read it, because it detaches your dimensions and you need to always keep your dimensions and so on. So what is happening is that, yeah, so not only does this read X-ray, so this X-ray read your NetCDF file, but you can also use, I think, GRIP and all the other data structures that you have. So here there's a lot of data. If you want to look at aerosols, you can look at air quality, you can look at atmospheric chemistry, you can look at it, or many other different parameters that you want to look at. For instance, in this case, I'm looking at rain or precipitation data from MIRA2. So I just choose precipitation here and so on. If you want to look at atmospheric radiation, you can choose. There are about 80 data products for that. For instance, in my case, I use this because I noticed that the community that is here is mostly people who want to do applied meteorology and climatology. So I chose rainfall for this quick demonstration. So here you can get that data. For instance, I'm using MIRA2, and so there are many different data products from MIRA2, as you can see, and even the spatial resolution and the time resolution of the data, it covers the whole world. Normally it will start from 1980 to now. All sort of data that you need is here. And so if you want, for instance, in this case, I'm using mantle data from MIRA2. So you can just go to subset here and you can choose your data. You can, okay, so you can download the original file. We can now go to, okay, normally when you do like this, it will be much better. And then you can just go to funny here, but yeah, you need to log in here, and then you can just go and specify your region of interest. Okay, the problem is I'm not logged in on this computer. So, but it will normally show you a place where you can just select the region of interest. You will see on my example, and then you download. What you will do is you will get very many files because you will have monthly data from 1980 to now for whatever grade you choose. For instance, for South Africa, if you want to choose for South Africa there. And but what will happen is that you will need to, you will get very many files and you can't download them one by one. So what I did is I wrote my small bash script that I use to download this data automatically that logs into this, put in my details and download the data. So that's what I did. So in all the data that you need, you do the same. So what I did is to download this Mirror2 data using the same method. So I'm using X-array. I'm also using CATOPy because I want to do projection. And I'm using Matplotlib also because I'll be plotting, and I'm using SciPy because I sometimes do stats on the data and so on. And this time color is for coloring my comments or my output message. Whenever I do something, you'll see how I use it. And this globe module helps find paths, in matching paths when I am directing my code to go to the path and extract that file and so on and so. And then this style here is, initially when I started using Python, I had to write my own plotting style, but I noticed that there's a scientific one where when you plot, you call it, and you'll have a very nice publication quality image. Maybe you should remove this so that it works. Okay, so that's that. And then maybe I'll restart the kernel so that I start running as I talk through my kernel. Okay, so we have cleared all the output from my kernel, so it means you must make sure that your libraries are able to run. Make sure they are installed. When you install them, of course, you can use QuantaForge, especially for this X-array and Oshino, and also CATOPy. Oshino helps with plotting oceans and all those nice colors when you are doing your plots. And then I'm doing statistics over my gridded data using Menkedal. Most of you may know what Menkedal does. It's for trend analysis on your data, because that's what most climatologists are interested in and so on. And I also call Dask, as you can see. Sometimes you forget to install some of these packages here in using this Anaconda prompt. So if that happens, then you can still install it here by just activating this and say pip install. You can also conda install here. You can also do whatever you want to do, but you need to put this in front of your line. So, okay, so it means I will run this package also that will be used to do trend analysis on my data, and then task as well. Okay, I just want to display my clients here. And then here I also put in a lot of information which you can use, including YouTube videos on X-array, how you use X-array and so on and so on to plot. When you give me a NetCDF file, in a few minutes I can do so many things with it, other than someone who may use maybe Graph or something like that. So Python has given this option to really not spend time reading or writing a code that you use to analyze existing data, but rather visualize the data or do some spatial analysis or some calculations on the data and finish it there. The color thing here is really painting the color that I do here. I painted blue, so it's a message. For instance, here I saved all my data files in this folder here. So if you go to this folder, it's let's go back one, data. So this is Mirror2 data. You'll see it is very many NetCDF files for each and every day. So for each and every month, starting from 1980 all the way to end of 2020. So that's the data that I'm using to make an example. So if you want to read one of those files or read all of them, you can use iGlobe and join them so that you can just quickly check how many are they here, these files that we are reading. So we have about 492 files here from 1980 to the end of 2020. So it can be any file, then you can read whatever type of file you want to read. It can be an output of WAF or an output of Geochem. I don't know what type of tool you use for modeling. But you can quickly, you know, with I said with X-ray, it's a tool that gives you the parameters that you may have downloaded, and also it keeps the dimension. So you don't need to always go back and define dimensions. For instance, here I'm now just looking at the first file that I read from here. So it means this is the file that is on top here, this one. So I'm just looking at it. Of course, Python starts from 0. And then, so this is the file that I'm talking about, the first file. Just, I want to maybe open it here. You can use XArray open dataset function, and then you put in the file that you want to open, and I'm opening it as mirror image global attributes, because I just want to check the global attributes. You can see here the data that I downloaded has, you know, what is nice about XArray is that it keeps these the coordinates, and it keeps your data variables that you have inside your NetCDF file, and it has these attributes where it explains what the data is and when it was processed, and many other things about the data, so that when you are writing a paper, you can always go back and check the level of data you used, and all sort of information about the data, because these data files are stored with a lot of details. And then so that's what you can do. So you can read one file and check what it is that is inside. Of course, the file has latitude and longitude and time. It's for 1 month, so time is 1, because it's just only this file. And latitude and longitude, my grid is 0.5 by 0.65 latitude and longitude, and so on. And the data that I downloaded is precipitation, total concentration, and convective precipitation. So just to look at it, those who are doing climatology would know better about what I'm talking about, of course. But this is just data for demonstration. So maybe what you want to do, you notice that when I read this data here, I use open dataset because I was just opening one file. But what if I want to open very many of them? That's when tasks come in. That's where I also, you know, if it is daily data, of course, I would have switched on the chunk. I just specify where the data is, and it ends with this. So the star means it will take everything before this sub. So if you have a file here, a file like this here, so I put a star here, so it will take all data that has this sub.nc in this file, and then it will read it. And so if I want to read them, so it will read all of them and chunk them, and it will concatenate them using time. So it means the first month with the first month, second month, and so on. So it will be like a box type of data, because it's better to work with this data in that way. So with NetCDF, I would have been required to write a loop that will read each and every one of these files and concatenate them. But with XArray, I just read all of them at the same time, and I have my data. So you can see here now, these are coordinates, it has time, it has longitude and latitude. And we also have data variables. You can see there's my precipitation, or convective precipitation here, and also my total precipitation here, and so on. And you can look at the data itself inside there. So the time starts from 1980, first month, all the way to the end of 2020. And you can also read more details about your data, latitude, and so on and so on. So for instance, if I click here, it can even show me what are the units that are there, and you can see this convective precipitation data. And if there are missing data values, this is what it will put. And so Vmax and Vminimum will definitely be this. What is nice about X-ray also, it does sort out this issue of missing data for you. Yeah, and then you can also look at the data, the size of the data, the shape of the data. Same thing applies to total precipitation. So, and then, you know, I think this is very clear and straightforward compared to reading this data using NetCDF file. I remember when I was doing my PhD, when I was viewing space, using space satellite data, and I was viewing this data, which was NetCDF file, I had to write a very long code that would assist me to do that. Okay, so let me choose maybe total precipitation. So the name of my variable is data. So this data has this in it. And then I just want to choose this one. So if I choose the total precipitation, then I normally, when I read this data, I know it is monthly and I know it may have gaps. What I learned when I was doing NumPy and Pandas is that every time you must make sure that your data is resampled into the sample that you need, because then it will always accommodate the gaps in the data. Again, when I was doing my PhD, you will get radar, HF radar data that will measure data in every second, for instance, or every 5 seconds or 1 minute and so on. And this data will have gaps, and you need to start to look for gaps. I had to write a very long code to look for data gaps in the HF radar, V and U data, meridional and zonal wind data. And that takes a lot of energy. So, but with Python, it is just only one line. So I think I wasted a lot of time. So I'm resampling this data into 1 month and summing it so that I calculate the total rainfall, of course, and I convert this into, you know, the units of this data is kg per meter squared per second. I convert this into millimeters per month by multiplying by 30 months, 24 hours, 60 minutes, and 60 seconds. And then this is how the data looks like. I even like this more actually because it puts a picture of the structure of the data. Just remember that even if you have height as well, because some data varies with time, latitude, longitude, and pressure level if you are in atmosphere, if you are in meteorology. But height maybe for us who are more of atmospheric physics people. And so even that data, you can read it and do whatever you want to do. Mostly you would want to be calculating molar plots and all the type of plots that you want to do for climatological study, or maybe for viewing Rossby waves, I don't know, and many other things that they normally do in atmospheric science. So this is how the data looks like. It varies with time, latitude and longitude, and so on. These are the coordinates and so on. So I did 2 convective precipitation and the total precipitation. I also convect my total precipitation. You can quickly view it, you can quickly plot it. And plotting in Python is much more easier if you are using X-ray than using NetCDF, because, you know, when you just pick, when I pick this variable, it brings its coordinates with. It means I can just say dot plot now and I can view the data already. without me labeling my x-axis, my y-axis, and this and that, because it knows it brings this with it. So, and then, well, then if you want to plot this, of course, you need to set up your figure. This is my figure size, and I just want to do a projection. I will use blade carry to plot, and then I will also set my extent. I just choose my extent over South Africa, of course. South Africa is between 22 and 35 latitude, 16 and 34 longitude. And then I take my data, I average it using time. You can sum it, you can do whatever you want to do. You know very well what to do with precipitation data. But already this data is in millimeters per month. So, and then you can take that, and then you can then plot that. I can then plot that data. I can define my bar, my color bar, put in the color bar label here, and so on. So here I'm just saying, I'm just taking this data that is averaged and then just plot it using color map rainbow and so on. And then here I'm putting features, so that the picture, the image looks presentable. I need to put coastlines, I need to put borders. I also need this short routine here so that I can put provinces in my map. And then I also put the title, and I can also add grids and define what color my grids are and what level of transparency should they be, and the line style and all these things. I think this is just plotting. If you like it, you can also use it that way. And that's why now I'm running it to take a few minutes, because it is a few seconds, because it is averaging my data and overlaying it on this projected map here. And so this is really a combination of matplotlib and so this is how it looks like. People who deal with total precipitation would know that, of course, we have more precipitation this side in KwaZulu-Natal, eastern part of the country. But maybe this is not the proper map to plot, because normally it should be the other way around. Precipitation, high precipitation will be like bluish, and low precipitation areas will be like reddish. When you notice how these meteorologists plot it, so you can just change here, maybe use spectrum. I use spectra to plot again. Okay, so maybe it's let me use jet. You can just Google CMap and choose very many of these color formats that you can use, and so on. But and so on. So here I was plotting total precipitation, and as seen by mirror 2, and here I'm plotting convective precipitation climatology average of the data from 1980 to now. So this is convective precipitation. Of course, it will be higher here around the warm oceans. Well, what you can do is to do a seasonal plot. If you want to do a seasonal plot, you will write a lot of loops when you are using NetCDF to read this data. But here, you can just plot this that you did here. And there is a function called group by. So you can group by time, season, you can group by time, months. So it means you can go do a monthly climatology. So it means we'll have 12 plots, for instance, for each and every month. But for me here, I want to have only 4 plots for different seasons, because it is important for climatologists to see which season has rainfall in which part of the country and so on. So this is how my data becomes like if I group by season and take an average of each season. As you can see, you can also open and check what seasons are there. You see we have TJF, JJA, so this summer, winter, and so on and so on. Autumn, and spring, and it will define what the data looks like and so on. By the time when you plot it, you know very well what you are plotting. What I did is to write a small routine that will assist me plot each and every one of these seasons side by side. So I just group my data and then I define my figure size and then I do a loop that will go to each season, plot it, and put in these features, set the extents and so on. So when you do this, so this is just basically plotting. You can also save the figure in this folder that I'm working with right now. So that means good, I'm here, so it will save this data somewhere here. So this is how it may look like after you plot. Of course, here I used, what did I use? Okay, I use spectra here. That's why you can see areas with higher rainfall with bluish. Of course, DJF is a bit rainy this side and drier this side, and Western Cape experiences rainfall during winter times and this time too. So you can do that. You can compare your WAF output, whatever domain you may have done, the bigger domain, and compare it with the output of Mira2 or CHIMPS. There's also another very high resolution rainfall satellite data or analysis data called CHIMPS that performs very well. And so on. So here I was plotting the convective precipitation and so on. Yeah, and then maybe let's quickly jump into Menkedal. So you can do whatever you want to do really with this data, as long as you read it using XRA. I hope you learned something. I was very quick when I was doing this, so I may have not removed these units here. These units here, because it is now millimeters per month. So, okay. So, well, when I'm plotting this convective precipitation, I extended this extent here so that it starts from the equator all the way to minus 35. So it starts from the equator to 35, so that you see the data that I grabbed when I was downloading from the disk data portal. So these are different seasons here, and so on and so on. So I stretched the extent a bit here. You can also change the projection and use whatever projection you like. You'll see on the planned talk that I have or demonstration that I have in 2 days' time that I use a different extent here. Okay, maybe let's. So I spent some time looking at a time series and plotting trends of a time series, maybe decomposing it so that I look at the variability of trend with time as a person who likes spectral analysis and so on. But lately I found out that it is much more faster and easier to go to each and every pixel of this map and calculate the trend and look at how the trend is in that pixel through what is called Menkedal. So this Menkedal here, there are many papers that can explain to you what this Menkedal is. They talk about different types of Menkedals. Here, I also attach this link. And from many years ago, the trend analysis using Menkedal has improved. Some people have modified it and used different methods to calculate it and make it better, where they put trend or they use pre-whitening method or they don't use it and use different methods, and they published a lot of papers. So all these apply in your trend analysis if you have a time series. So that's what I'm using here. So, well, when I did this trend analysis using R, because I also code using R because it's a statistic, it's this work is actually more on stats of the data and so on, and maybe single spectrum analysis and so on. R does this better. But when you have a map like this, I found out that if you take your data, put it in this Menkedal function, choose what Menkedal you want. I want a modified one. So I'm saying modified 2, and the method of calculation and the confidence level, p-value. I can calculate what could be the trend for each and every pixel in my data. So for each and every pixel, starting from 1980 to now, monthly mean, what could be the trend in each and every pixel. So you can do it for instance, an example here, it is for convective precipitation and so after you run this, you can just compute. You can, if you run this line here, you can get a lot of details about Menkedal test itself. So when you forget what outputs does it give you. The mathematics of Menkedal is very, very easy if you look at it in these papers. So they even give you an example of how to do it and so on. So that's what I followed when I do this. And then you can display the output of your Menkedal. You can see here we have the trend, the significant, and p-value, standard error, sorry. And you can quickly check here what are all those. If I'm talking about p-value, I'm talking about the significance test of the trend. There is even candle down. You can also get S, which is the Menkedal score, and you can get a slope. You can get a trend, which will tell you the increasing or decreasing trend over your image. So that's what this is doing here. So I have my output. I can just select any of these and maybe plot it here. Look at the trend. So if you look at the trend, you'll notice that. So what is this one? Okay, so I'm calculating the p-value. P-value is much more higher in these areas, which means it is much more significant in these areas here. It is much more lower, which means the trend is not so significant in these bluish areas here. And so on, you can change here and plot your, where does that help? If you think in KwaZulu-Natal, we have a significant decreasing trend of rainfall, then this should explain that yes, that decreasing trend of rainfall that you may calculate, for instance, from station data, it is significant, or that you calculate from the data that I use here using Mira 2, it is significant, and here it is not so significant. But what you can do again is to go to maybe first 10 years, next 10 years, you demarcate your data into 10 years because it is easy to slice your data. This is an example to slice my data, for instance, because here I wanted to pick maybe a time series that I can compare with the ground-based data. I'm sure you'll be happy to also see how does this satellite data compare with the ground-based data. So you can demarcate this data into pieces, and then you can look at every 10 years, how is the trend. I can tell you around the Eastern Cape here, the trend is much significant downwards. So you notice that even today, there are some areas which are still dry there. But here we are a bit wet recently. We've received a lot of rainfall. Yeah. Okay, so with XRA, you can also select a certain time period by just saying time slice, and you can just pick data from 1995 to 2020. I'm picking this data because I want to use ground-based data from Hermanus. Hermanus is somewhere here. Okay, I'm using this data because I spent my PhD there, some 3 years there doing my PhD. So the data that they were collecting there, I always, saw how they collect and quality checked it. I just want to compare this data to what I see using the satellite. So if you slice this data, you can see it is much more shorter in terms of time now. It is 1315 because I cut out the time series from 1980 to 1994 because the data in Hermanus starts from 1995, which means I can do that and go to the pixel that is closest to Hermanus. So I can go, these are latitude and longitude of Hermanas. So if you want to pick the latitude of data that is closest to that, the latitude and longitude position that you want to do, you need to just select and then define the latitude and longitude and then use method nearest so that it picks it. And then, so it will have that time series. So you will have that time series. So that's what this is doing. So what I'm doing, I picked that time series over Hermanas and then I plotted it at the same time, just to view it. You see, we remember the day zero time here after 2016, you can see there is this. But if you decompose this using maybe EMT, which I wanted to show here, but of course I can't get there, you will notice that the trends change over time. That's why I say, if you want to see these trends properly, you must demarcate your data to 10 years, 10 years, 10 years, and calculate trends for each and every one of those 10 years all the way to now. And so on. So this is the data, and this data I want to make it a data frame, because at the present moment it is not a data frame, it is an XRA data set. For me to be able to do what I can do using pandas data frames, I need to convert it to a data frame. So what I do is I just take this data and make it a pandas data frame. And then I can do whatever I want. It will look like something that you are familiar with if we have handled data or did a bit of data science using Python. So what it does, it grabs latitude and longitude as well, but it takes total precipitation, and these are different years here. And of course, right now my time is my index. So you can reset time as an index, because sometimes when you choose your parameter, it automatically chooses the time if the time is indexed. So I just reset the index here. So now the index is this one and time is available. So, and then I did this because I wanted to change this name. I don't want it to be time, but I want it to be date maybe. And this precipitation, I wanted to be rainfall instead of precipitation. I'm sure those who did data science will understand this much more better. So I'm renaming my data frame now. Just renaming these two. And then when you go to the rainfall, okay, this is just to view the rainfall. And then this is a small routine that I did for climatologists if you want to view a box plot of all the months or yearly data, and also the seasonality of the data. So it's a straightforward plotting and how you choose your data and do a subplot of box plot and a point plot, and then use Seaborn. It uses Seaborn, as you can see here. It uses Seaborn to plot, and then I'm just using it here. So I'm taking Hermanas data and plotting it using this small function of mine. Okay, maybe I can share this if you like it. So this is each and every year you are plotting a box plot, and you can see here rainfall is much more in winter time, Hermanas and something like that. So be quicker because of time. And then okay, and then okay, so here I'm just checking what type of data structure is this, and maybe more information about my data structure. This is just to inspect your data and check what exactly you are dealing with in your time series and so on. So here I just want to calculate SPAY. SPAY is a standard precipitation index. I want to calculate SPAY using this data maybe. Say if I want to do that, then I would need to maybe reset the index, or maybe calculate my own index that I can use as an index of each and every month data. So my data starts here and it ends in 2020, but of course it must end in 2021 if you are using this routine. And then so it will add this index that I've calculated. And then I can just choose this, and then it will take it with the index. And then I can just define, this is my routine that I wrote using SPAY, which I read in a paper, which explains different steps to calculate standard precipitation index. It is used to identify, meteorological drought, and you can also identify signatures which are associated with long-term drought. It depends on how you calculate it. If you smoothen it with 3 months, then you are most likely seeing short-term dryness in that area. If you do spay 12, for instance, then you see longer-term dryness in those areas. So this routine does that. I think I may have forgotten to put the paper that I used to write this nice routine. And then, so here I'm calculating space 12 and space 6. So I'm applying my function right now. And so this is the data. Of course, this is a rolling, it uses rolling average. That's why you will have the first 6 values not there. Maybe the first 12 values not there. And then you have your space value. And then you can just plot that. The aim is just to plot that. Plot it here. Of course, here I use a loop to plot it because I wanted to plot both of them in the same field. So it goes to this data frame and chooses this one and then chooses this one and perform the same thing. This is how it looks like at the end. The reason why it looks nice is because of the plotting style that I use. So this is Hermanus. You can see the recent extended drought around the Cape Town area as signaled by Spain, and you can see some episodes of dryness that may happen in a shorter space of time, and some wetness that may happen. So this assists to track drought in areas. What I've done also, okay, I don't have time. I think I have 5 minutes. I just want to demonstrate quickly how you can quickly compare like a time series of Hermanus with a time series or Hermanus measured in the station there, rainfall, and then maybe data that is calculated from the Mira2 that I'm using here. So in this part here, I'm doing that. So I'm reading ground-based station from Hermanus. So this is the file. I sourced it from the South African Weather Services. And you can see it starts from 1995 and so on and so on. And of course, I need to pre-process. You'll notice that here the time column is not there, but they give you month, year, and day. So I need to take this month, year, and day and calculate my data. So this function, this pandas function, asks you to go to data. You select year, month, and day, and it will calculate for you the data. And then so now I do have the date which I calculated here and so on. And then here I set the data as an index. Of course, there's also temperature and other things. And then I resample my data. I told you that I normally resample my data so that it increases the gaps that are there in data. And then I can have a quick plot just to view my data. So this is how it looks like with month total rainfall. So this is normal Python plotting, just a quick plot. Of course, it will look nicer because I use the plotting style that I defined on top. And then I need stats model and scikit-learn because I need to create a small model, linear model, to find the linear relationship between the K-point, the Hermanus data, and the Mira2 data that I took in a grid over Hermanus. So you can have data from the Hermanus. So this is the data frame from Hermanus. You must make it an array, and then you can have an array of data from the Mira2, which is total precipitation. And then you can create your model using stats model here, fit the model and do the prediction, and then you can check the summary of your model, and then using scikit-learn, you can thereafter print these model performance statistics, but in this case, I'm just comparing ground-based data and satellite data, the root mean square error, mean square error, and all those things, including correlation and all those things. So in this case, I can see that the normal squared R is this, but the adjusted one is this one, is about 0.77. So this is, and then this is mean square error and other test parameters that you can use to look at how the two time series compare. So this you can do, for instance, if you have a WAF model, you want to compare, or say you model, you look at the cloud burst, you have a time series from a ground station, you can thereafter take that ground station and take the output of your WAF, pick the grid over your desired point and compare it using these statistics. So it may be longer when you're using other methods, but it is shorter, and I can share with you if you like. So maybe now it's about 10:29 according to my watch, but I had some other things that I can share with you later if you want to see, including how you can use Fourier analysis to look at periodicities in the data, and also later, and then I demonstrate just an example of how you can use FFT. I remember when I was doing MATLAB, I had to write a bit of a longer code, but I just converted my MATLAB code of spectral analysis to Python, and it worked very well. For instance, if you have an artificial data, if you create an artificial data, a combination of signs, you put in known frequencies just to test if your FFT is working properly. You create a sinusoidal signal like this, and you then after perform the FFT of that signal and so on, and plot it. Are you going to get exactly what you inserted in terms of your frequencies? So before I use this on the real data, I need to test it here, create something that I know very well what I feed in, the time, the frequency that I feed in, and so on and so on, and then check if I can use FFT to take this time domain here to a frequency domain, so that I identify the frequency that I need for analyzing or for checking the periodicities that are there in your rainfall or whatever time steps. So after this, then you can just use the same FFT routine on your rainfall data to see what periodicities are inside. From here, you can thereafter use wavelets to look at this in terms of a 3D dimension. So wavelets are very good also analyzing geophysical data. That's that, maybe because I don't have more time, and maybe I can stop here.
Okay, Dr. Mbatha, thank you so much. You had a little bit less time than planned, but you managed to squeeze in a lot of information for our participants. Thank you very much. It was a very informative and enjoyable lecture. Thank you so much. I know we already are over time, but maybe if there are a couple of urgent questions, we can take them. So please just ask the question. Yeah. Or if you have comments or suggestions.
I think Erika is asking if I can do. Yeah, it's a small bash script. Of course, if you email me, I'm sure my email details. Let me write my email here.
And Dr. Mbatha, we have also for the school a Moodle account. So if you want to share, for instance, your slide, your notebooks with me, we can upload it to the Moodle account, and everybody will have access to it.
Oh, okay. Yeah. Okay, no problem. I don't know. I'm sure others used Bash script.
Yes,
I use Wicket on my Bash script. I have it in my Linux computer here. I would have shown you quickly how this Bash script looks. It's a small script, but you cannot download this data one by one if you want to do that. So you need this small script, which I can share with you.
Thank you very much. Eric, I see your hand is raised. If you would like to add to your question, you're most than welcome.
Thank you very much, and thank you, Dr. Mbatha, for such a wonderful presentation. I was just thinking maybe Dr. Mbatha will need a week actually to go through
Okay.
all the stuff that he has. It's a very wonderful.
Yeah, sorry. I'm sorry about that. Yeah. Well, what I can do is to compensate this, but you can contact me, and then I can. Well, I have several guys that I'm working with who are doing oceanography. They want to view this applied mathematics they use to calculate waves and stuff. So mine is to help them view the data and do whatever they want to after they do computation in supercomputer and stuff like that. So I'm always free to. You can just contact me. We can just go through what you need to do with your graded data.
Yeah, but my question to you, Dr. Mbatha, is you mentioned that you are a self-taught Python user. And I'm almost like in the same shoes, almost self-taught, and I've been trying for a couple of years to really get into Python. So you get to learn Python, you know the syntax a little bit, but you don't get to the point where you do something realistic with it. So what is your advice to get to a point where you can actually do something meaningful without just small scripts or small syntax issues, and that's it. It ends there.
Well, when I did Python, I started with Fortran long time ago, and then I moved to MATLAB because I was doing signal processing most of the time for my PhD. And then, so when I do Python, I already know very well what I want to do. So you can spend some time learning the syntax, but don't think you are learning how to program if you are not giving yourself a problem. So you must have a problem that you want to solve, and then you must find ways to solve your problem. That's what I noticed, because actually what I'm doing more on Python is machine learning, where I'm doing time series forecasting, because signal processing started to be boring to me. Doing single aspect. And so I'm doing LSTMs and forecasting a time series and CNNs, because when you do, another thing is that every day when you leave your day without doing one or two things, then you forget. But the bad thing about doing MATLAB, JavaScript, this and that, is that sometimes I take what I do in MATLAB and write it here and only realize in a few minutes that no, this is not, this is maybe R, or this is this. I think you must give yourself a problem and practice that problem, other than learning pandas and NumPy and all these small things.
Yeah. Excellent. That, I think, is very good advice. Yeah. And Krishna, I see you added a long comment in the chat. Yes. Would you like to share it with us verbally?
Yeah, I was just giving a comment to Eric that don't expect to just do stuff immediately with something big, because if you're going to go that route, unfortunately, you're not going to get anywhere. You should start with small scripts and then just try and add complexity to it as you progress.
Yeah. Yeah, no, thank you very much, Krishna. That I think the combination of both your advice is very precious. Yeah, nothing beats doing it yourself, but you can't start if you're new with too ambitious projects. Just start small and build it up. Yeah, and it will work. Once you have something that works, you can modify to become a little bit more complex, and at least you can always go back to something that works. Yeah? Otherwise, if you start with something that doesn't work and is too complicated, you might never be able to get it up and running. So start always small and build it up. Yeah. No, thank you very much, Dr. Mbatha. It was a very enjoyable lecture. And thank you that you tried hard to catch up. But it's absolutely fine. I think everybody enjoyed it very much. And I think people would be very keen to if you could share your scripts, your code, so that to make their start, their activities in this area a little bit easier to start. Yeah. So thank you very much. Maybe let's conclude with the usual adverts. Yeah. This afternoon at 2, we have lecture 4 on the introduction to statistics with R, yeah, by Christine Kramwinkel. So please join us again just before 2. And the next lecture of Dr. Mbatha, sorry, I need to check, is I think on Thursday afternoon. Yeah, so Thursday afternoon at 2, we have the next lecture of Dr. Mbatha. Yeah. So and I will make sure to have the cell phone number of Dr. Mbatha.
Okay, no problem. Yes. Yeah. Then on Thursday, maybe what I remember that there is I wanted to do something realistic with the data that is much a bit more.
Yes.
Yeah. So what I will do is I will look at atmospheric chemistry using a satellite called Topomi Sentinel P5. I will look at the pollution that happened here in Durban when people started banning things when they were protesting for Zoom. So that's what I want to do on Thursday. Maybe in a bit of wavelet analysis of a time series.
Okay, that will be very, very, very interesting. That will be very that lecture. We could also, at a later stage, invite you to speak at the NITheP colloquium, because that's a topic that will interest lots of people. Also outside the school, if you give it a slightly different character, not so much of a schoolish one. Yeah, but we can discuss it on Thursday. That's very interesting. Thank you very much. Thank you. Then everyone, thank you very much for your presence this morning, for the comments, for the questions, for the discussions. And I really enjoyed the first half an hour when we chatted a little bit about various issues. So you see that everything comes with a purpose. And I will see you later at 2 o'clock this afternoon. Thank you very much, everyone. Have a good rest of the day between 2 o'clock. Thank you. Bye-bye, everyone. Thank you very much. Thank you, Dr. Mbatha. Really much appreciated. Thank you. Thank you.